Since the late 70s. Scientists from NASA have been flying near the hole, doing research to try to find out why the hole has appeared. Many scientists believe the gases used in aerosol cans and refrigeration units, known as chlorofluorocarbons, are mainly responsible. In the upper atmosphere, sunlight breaks them down, releasing chlorine, which interacts with the ozone in a complex series of chemical reactions and destroys it. In today's Nature magazine, scientists reveal more evidence implicating aerosol gases.
There is a very important signal being given to us by the disappearance of ozone in Antarctica. It's a signal that we really must be concerned about. If this was to spread to the rest of the globe, the consequences would be devastatingly serious.
One estimate suggests that if the production of chlorofluorocarbons increases by 3% a year, there could be 3% less ozone in the atmosphere by the year 2000. There's still no final proof that aerosol gases are to blame, but some would argue the world should take action now. And in Montreal, a meeting of the United Nations Environment Programme is discussing freezing the amount of these gases that are being produced and eventually reducing them.
In the late 80s, detection of ozone holes around the poles led to concerns that too much UV radiation was reaching the surface of the Earth, leading to skin cancers and the like. The problem is linked to the presence of chlorofluorocarbons, CFCs, in the stratosphere. The sun's radiation causes the carbon-chlorine bond to break homolytically, giving chlorine radicals. These react with ozone to give oxygen and chlorine monoxide. The chlorine monoxide then reacts with oxygen atoms present in the atmosphere to give back the chlorine radicals. The fact that chlorine is regenerated means it can react again with ozone, and so the cycle continues, reducing the ozone concentration. Even if CFCs were suddenly withdrawn, they would still leave a long-term legacy. Reservoirs of hydrochloric acid and chlorine nitrate, which can continue to slowly release chlorine.
Reversing that.
International agreements have led to the planned phasing out of CFCs over the next 10 years.
It confirms that the ozone layer is being damaged by CFCs and other chemicals.
In 1982, a major eruption took geologists and climatologists by surprise.
El Chichón confirmed the basic mechanism through which volcanoes affect climate.
Within days, it provided information to almost every atmospheric satellite that orbited the Earth. Initially, the cloud of volcanic ash from El Chichón in Mexico was tracked successfully by the NOAA weather satellites. It can be seen clearly fanning out before being dissipated by the wind. But infrared images revealed something else rising above the ash cloud, a plume of gas. Within 21 days, the plume had been carried around the globe in a thin equatorial band. It left behind a trail of dazzling sunsets across the Pacific and back round to the USA. The optical haze was measured using LiDAR, firing laser beams at the sky and timing the reflection. There was aerosol in the stratosphere, scattering sunlight. When geologists reached the crater, they discovered that El Chichón was extraordinarily rich in sulfur. and that confused the satellites too. Instruments designed to measure every aspect of the atmosphere found their readings going haywire. The total ozone mapping spectrometer picked up what seemed like a massive hole in the ozone layer. In fact, it was the backscatter of light by sulfur dioxide. The volcanic gas was tracked around the globe until it faded. It had been converted to sulfuric acid. Samples from the stratosphere were picked up by flying through it. They found sulfuric acid droplets. NASA's advanced very high-resolution radiometer, designed to monitor the temperature of the sea, mapped the cloud for the longest time. For 6 months, the cloud hugged the equator near the latitude of El Chichon. Over the year, it drifted towards the North Pole, thinning as it spread through the stratosphere. From global readings of optical thickness, they got a total mass of sulfuric acid aerosol mixing in the stratosphere. At its midsummer peak, estimates were of 20 million tons. After 6 months, it started to decline. By the end of 1985, after 3 years, the aerosol had virtually disappeared.
Tremendous amount of information resulted about the nature of the volcanic cloud, transport in the upper atmosphere, and the manner in which the energy balance is affected. And of course there was very hard data concerning the warming of the upper atmosphere following this event. So the basic mechanism of the volcanic impact on climate was confirmed.
But what also showed up was not quite as predicted. The temperature trend for the 80s was a steady warming. Yet in 1984 and 5, there was significant cooling.
But it's very interesting that we do detect in this case this long-term cooling, which presumably is due to the thermal inertia of the oceans, the fact that the oceans take time to cool down and delay the overall impact on the climate system.
When they ran their regional model patterns again, that delayed temperature drop 2 to 3 years later appeared in certain regions, the northeast USA and Europe. The computer models of the effects of El Chichon did predict worse winters in 1984 and 5. We got them. It seems that volcanoes bring a long-term and more sinister side to the familiar suffering they have brought to humanity. Mick Kelly wonders how much the computer models can be trusted.
We were quite taken aback by the results of our analyses. This rapid drop in temperature within a couple of months of a major volcanic eruption wasn't predicted by the numerical models, by our models of the climate system. And this raises the possibility that these models are not complete, that there may be surprises in store that these models aren't telling us about. Take, for example, the greenhouse effect. Our models predict gradual warming over the next 30, 40, 50 years by a certain amount. Now, this may well be true, but it's also possible that the warming may occur in fits and starts. And when we look back at the warming that's already occurred since the late 19th century, this in fact is what we see. A net warming of around 0.5 degrees Celsius, consistent with model predictions, but not occurring gradually, occurring rapidly during the 1920s and 30s, a period then of relatively stable temperature, and then more rapid warming during the 1970s and 1980s. So there may be surprises in store, and I think the volcanic analysis warns us not to place too much faith in our models of the climate system at this time.
In Colorado, the National Center for Atmospheric Research, NCAR, has one of the most powerful computers in the world. Researchers throughout the USA use it for modeling the climate. After El Chichón, it modeled the complex reactions of oxides of nitrogen and CFCs involved in ozone chemistry. A layer of ozone in the stratosphere protects the Earth from ultraviolet radiation. Colored purple here, a hole in that layer has been revealed over Antarctica in recent years. As the pole moves into sunlight every spring, ozone decreases dramatically. Now it's happening in the Arctic too. Ozone is broken down by chlorine monoxide, created from CFC pollutants, only on the surface of stratospheric cloud droplets. Stratospheric clouds naturally occur only over the poles, and so the ozone holes appear there too. But there is another source of stratospheric cloud. The sulfuric acid droplets from El Chichón created as much stratospheric cloud as already existed over the poles, but it was spread throughout the hemisphere. Atmospheric chemists predicted ozone depletion. The NASA instrument that tracked El Chichón's sulfur cloud was also monitoring ozone. Its data are very clear. As El Chichón's aerosol cloud increased, ozone levels fell. The eruption of Mount Pinatubo that devastated the Philippines in June 1991 finally confirmed the theory. Another decade of CFCs pumped into the stratosphere had stored up a chemical time bomb to await the volcanic trigger. This winter, the European Arctic Stratospheric Ozone Experiment began a series of balloon flights into the stratosphere from a base in Sweden. They traced the volcanic aerosols and also the chemical effect of them.
The measurements that we've made during this winter's ozone campaign have shown a tremendous influence of the eruption of Mount Pinatubo. In particular, what we've seen is very, very low levels of the oxides of nitrogen in those areas where we're also measuring high levels of sulfate aerosol, this coming from the eruption of the volcano. Now, the importance of this is that the oxides of nitrogen normally would inhibit the chlorine catalyzed ozone destruction. In other words, if we have no NOx in the stratosphere, and we're seeing very low levels indeed, if that isn't there, then if we have chlorine compounds, they can destroy ozone so much more efficiently. And that's what we think is happening during this winter and spring.
Backtracking the weather in the polar vortex, they put in known values of chemicals and the stratospheric clouds and ran a model to see what the chemistry produced. It predicted a 10-fold increase in chlorine monoxide over northern Europe. Last September, NASA launched the Upper Atmosphere Research Satellite. It measures the chemistry of the stratosphere. The satellite measurements showed a great similarity to Pyle's theoretical predictions. Sitting over northern Europe in the new year was a mass of chlorine monoxide sufficient to deplete the ozone layer at a rate of 1% per day of sunlight.
What we saw in January was a very serious situation indeed. It seems to me that the conversion of chlorine to the forms that could destroy ozone happened as efficiently as it possibly could.
By mid-February, the concentration of chlorine had reduced due to the mixing of different streams of air in the polar vortex. Ozone levels are more complicated to calculate, and NASA will release its data soon. So far, there is no catastrophic fall in ozone this spring.
Nonetheless, I still think that we're probably having quite high levels of chlorine monoxide in now the middle and high latitudes, still enough to sustain reasonable amounts of ozone loss. I think that when we come to analyse the data properly at the end of this campaign anyway, we will see that ozone levels are pretty low. I'm pleased that we don't have a great big ozone hole over the Arctic. I've never said that there would be one. What I do think is that we will see ozone levels this year which are probably as low as we've ever seen them.
The mixing of the weather system saved us from an ozone hole this time. As a foretaste of the future, video from those living under the Antarctic hole has been released by Greenpeace. In Chile, it is thought to be causing increased malignant skin cancers, barren grasslands, and sheep barely able to survive with cataracts and eye infections. The warning sounded in January has spurred calls to phase out CFCs earlier than planned. Yet what we put into the atmosphere now will only begin to destroy ozone at the turn of the century. Until long after then, we'll have to hope for no large volcanic eruptions.
This winter's phenomenon was one where it was a combination of a man-made effect, the release over a couple of decades now of these chlorofluorocarbons, building chlorine levels up, and a natural phenomenon. And we cannot regulate the natural phenomenon. So if we want to try to protect the ozone layer, the thing that we have to do is to make sure that we regulate the man-made part of the problem. We can't do anything about the volcanic eruption.
NASA's Upper Atmosphere Research Satellite, S9ORS, is the first mission totally dedicated to investigating change to the upper atmosphere, including processes that lead to ozone depletion. It's the spearhead of NASA's mission to planet Earth and begins a comprehensive study of the upper atmosphere. From its vantage point in space, S9ORS provides near global coverage. This orbit lets instruments distinguish between short-term daily and long-term seasonal effects and permits a view of ozone depletion over the poles.
An international team of scientists assembled this year in an emergency effort to make a detailed study of the North Pole. Most of the work was performed aboard 2 NASA aircraft. This is the ER-2. For the mission, special wing pods are attached containing atmospheric chemistry analysis equipment and a host of other instruments. Typically, flights are made about 12 miles up, along the fringes of space, right into the layers of atmosphere directly affected by ozone loss. Inside, scientists perform their experiments and are able to map results right on the spot. This instrument contains 4 lasers capable of shooting light many miles up into the atmosphere. The light reflects back to the plane and provides scientists with a cross-sectional map of ozone concentrations as well as aerosols, or regions where ozone depletion is capable of occurring. Initial results indicate that high concentrations of CFCs have been found at northern latitudes, primed for ozone destruction. Thanks to the intensive work done in the last few years, we know why ozone depletion exists. It is now up to the world community to take responsibility for the future of our global environment.
Venus is Earth's sister planet and our closest planetary neighbor. Despite its nearness, however, Venus remains a mystery. In 1989, a spacecraft named Magellan will be launched to Venus. After a 15-month-long journey, it will begin mapping the surface of Venus with an innovative imaging radar system called Synthetic Aperture Radar, or SAR. In its primary mission, Magellan will map at high resolution for one full Venusian day, which is equivalent to 243 Earth days. Magellan will be inserted into an orbit that will take it around the planet every 3 hours and 9 minutes. Each orbit will include a 37-minute data gathering period beginning at the North Pole and moving southward, viewing a 25-kilometer wide swath to about 68 degrees south latitude.
In 1991, Magellan arrived, started taking pictures and sending them back to Earth.
The orbit strips that it returns are about 20 kilometers wide and about 10,000 kilometers long. What we do here on the ground is we take these strips that Magellan gives back. Every day it gives back about 7 of these strips. We take these strips and we put them together into a mosaic such that you aren't looking at through a picket fence, let's say, at just one small piece of it. So on the ground, we take the computer to come and put these swaths together. As you can see, here's one strip or swath, and here I purposely skipped one, and then here's the next one, which would be orbit 386. If we continue to put these orbits in the frame, you can start seeing a wider peripheral view of the planet. And as we fill it in, we see an impact crater on the surface.
As well as taking flat pictures of the surface, Magellan uses its radar to measure the height of the land underneath it. Computers put the 2 bits of information together and produce a real 3-dimensional picture of the planet's surface. Join them together and this is what you get.
Help us learn why Venus, our sister planet, has evolved so differently from Earth, and by comparison give us insight into our own geology and climate. In April 1991, NASA deployed the 17-ton Compton Gamma Ray Observatory, the largest instrument ever launched into space. This great observatory sees the high energy end of the spectrum that holds encoded information about quasars, galaxies, and black holes. The Compton Observatory seeks answers to baffling questions about the origin and future of the universe.